Hi, my name is okuno from the Institute of Statistical Mathematics and Riken AIP. Today, I'm going to talk about generalization gap estimation for overparameterized models via the Langevin functional variance. This work is joint work with Professor Yano of the Institute of Statistical Mathematics, and our paper has been uploaded to arXiv. So if you are interested in this talk, please refer to our preprint. Okay, anyway, let's get started. Okay. First, the purpose of this study is estimating the generalization gap efficiently for complex models, such as overparameterized models, including neural networks. As many of you may know, the generalization gap is defined by the difference between the test error and the training error. For instance, for regression problems, the generalization gap is defined like this equation, delta. The first term here represents the test error, meaning the loss function for newly generated outcomes y star, and the second term represents the training error, meaning the loss function for the outcomes used for training the regression models. If this generalization gap delta is small, then the trained model is expected to perform well, even for prediction problems for newly observed covariates. So in this talk, we especially consider estimating this generalization gap delta only from the training data for overparameterized models. Okay. Actually, there exist several methods for estimating this generalization gap. For example, cross-validation is an approach for such a generalization gap estimation. In this slide, I show leave-one-out cross-validation. Okay, and the cross-validation, which we denote as CFV here, is proved to be a consistent estimator for the generalization gap. But the cross-validation here is computationally intensive for overparameterized models because computing cross-validation requires optimizing the regression model several times. Instead of this cross-validation, we may employ an information criterion. For example, AIC penalty is defined by the number of parameters in the regression model, and TIC is defined by the trace of several matrices derived from the Fisher information matrix of the regression model. Actually, these information criterion are easy to be computed, but their theories are proved only for the regular models. So these information criterion cannot be applied to the overparameterized models because the overparameterized models, including neural networks, are usually singular. So to estimate the generalization gap for the complex models, in this talk, we employ a functional variance, which is also known as WAIC penalty, proposed by Watanabe 2010. This criterion, WAIC, is a kind of singular extension of AIC. So this criterion can be applied to even the complex models, but there remain several problems on this functional variance. Okay, and the first problem here is that the existing theories of functional variance is proved only for the fixed size of regression models. So the theories of the functional variance cannot be applied to the overparameterized models, including neural networks, because overparameterized models contain many parameters. So overparameterized models, including neural network, is not the fixed size of models. Okay, and regarding this first issue, we proved the statistical consistency of the functional variance for a linear approximation of overparameterized models. So we partially generalized the theories of functional variance from the fixed size of models to the overparameterized settings. But in this talk, we skip the details of this first contribution due to the time limitation. Okay, and the second problem here is that the parameter posterior used for computing the functional variance is computationally intractable for overparameterized models, especially for neural networks. To compute the posterior, we employ Langevin dynamics, And we propose a Langevin functional variance which can be computed efficiently by using existing Python packages. So in this talk, we focus on the computation of the functional variance using the Langevin dynamics. Okay, here I show the formula of the functional variance. Functional variance is defined like this for regression problems. Okay. To compute the functional variance, we need to compute the posterior of the regression model parameter beta. The problem here is how to compute this posterior efficiently for complex models, especially neural networks optimized by stochastic algorithms. Okay. Key idea here is to utilize the Langevin dynamics. Please look at this figure. We utilize some overparameterized models. Here, we especially consider neural networks. Then we optimize the neural network by using some gradient-based approaches, such as SCD. So we denote the SCD sequence by beta. Then after the convergence of SCD, we start the Langevin gradient descent defined by this equation. As you can see, the Langevin gradient descent is defined by the sum of the simple gradient descent and the normal perturbation. Then it is known that the empirical distribution of the Langevin gradient descent sequence approximates the posterior. So we can replace the posterior in the functional variance by the empirical distribution of the Langevin sequence. So this is our key idea. So as this Langevin sequence approximates the parameter posterior, we may replace the posterior in the functional variance by the empirical distribution of the Langevin sequence. So we propose a Langevin functional variance by this formula. This formulation is very simple and it is computationally efficient. Especially this computation requires only the first order gradient, but not the second order gradient. And this formulation requires only the gradient, so the Langevin functional variance can be implemented very easily by some famous Python wrappers such as PyTorch and TensorFlow. So here I'd like to describe the numerical experiments on this Langevin functional variance. Okay. At first, I'd like to describe the results of experiments of high-dimensional linear regression. In this experiment, we consider the high-dimensional regression with the setting that the number of parameter p is twice as much as the sample size n. Then, as you can see, by increasing the sample size n, the value of the functional variance, this one, and the value of the Langevin functional variance, this one, are roughly 9. And these values are compatible with the generalization gap delta. So namely, the Langevin functional variance approximates the generalization gap even for overparameterized settings in the high-dimensional linear regression problems. Okay. Actually, the previous experiment is for a linear regression problem, but from here I'd like to apply the proposed Langevin functional variance to the nonlinear neural network. For this neural network experiment, we employ a free connected one hidden layer neural network G theta defined like this, which is activated by the hyperbolic tangent function. And we define the empirical generalization gap by using the synthetic dataset. Okay, the result is like this. In this experiment, D denotes the covariate dimension, and M denotes the number of hidden units in the neural network. Roughly 1,000 parameters are included in the neural network. And as you can see, for most of the settings, the proposed Langevin functional variance roughly approximates the generalization gap delta. For example, here, as you can see, the Langevin functional variance is roughly 20, and the generalization gap is 90. So Langevin functional variance roughly approximates the generalization gap. Okay, this is our conclusion. Thank you very much for listening.